Today is November 26, 2022. This is my 144th episode for C++ 17 2023 CUDA SYCL OpenGL OpenCL TBB Vulkan. This is 9th episode for advanced recursion, parallel numerical derivatives, parallel numerical integration. I finally implemented parallel partial derivatives with TBB and SYCL. I filmed this video for my own future reference, not for my audience, if any. I basically used 7-point stencil algorithm for numerical derivatives. In this video, I derived 7-point stencil algorithm based on 5-point stencil algorithm. Also, I implemented partial derivatives, gradient vector, line integrals, etc. in this video. I got the source code for derivatives for CPU implementation from this video. If you haven't upgraded Intel Data Parallel C++ compiler to the latest version, please watch this video. You, in this case, is not my audience, but future Thomas Kim. We need to set up environment variables from Visual Studio, New, Project, search for DP/CPP, select Console Application, click Next, Create, right-click the project, Properties, select VC directories, include directories, edit, copy this path, paste it in your editor. We will delete this part because all other paths include oneAPI. Delete. We will change this dates to latest. Copy, paste. We can remove Intel 64. This path does not exist. Delete it. Also, we will fix like this. Now, semicolon, 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 semicolon. Here, right-click, search, environment, environment variables, new, dp/cpp underscore inc. We will copy, paste, then copy, paste, then copy, paste, copy, paste, copy, paste, copy, paste, copy, paste. Click OK. Now open it again. Click Edit. You have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Now we can close it. Click OK. Click OK. Click OK. Now we can close it. Open up Microsoft Visual Studio Code CPP 1720 145. We don't need this folder. Delete. Remove to recycle bin. In the folder 145, click this button, generic parallel partial derivative.cpp, hit enter, Ctrl B. I will copy and paste this text. Now here, void test partial derivatives TBB int main, copy this, paste it here, string hello generic parallel partial derivatives with TBB and then open up this command prompt in the our working directory. Copy the path cd paste dir dp cpp qscd c++ training. Don't miss EHSC general parallel partial derivative.cpp od.exe, hit enter. It should build and run successfully. Copy, Control Home. We will paste it here. Please notice the squiggle. Ctrl Shift P, edit configuration JSON. We need $dpcpp inc, then 2 comma. Now this should work. We test the hello generic partial derivatives with TBB. I will remove hello, then enter. For app, we define arbitrary function x, y, z, semicolon, return x times y times SED sin C. So we defined one lambda function. Copy, paste. Now this is fx. We differentiate this function with respect to x. So it can be 2.0 times x. We can do differentiation once again. It is f(xx). We differentiate with respect to x once again. Now it becomes like this. Please notice the position of variables x, y, z. So 0, 1, 2. 0 represent variable x. 1 represent variable y. to represent variable z. Now, here context for auto dx sed index sequence 0. It should be instance partial derivative with respect to x. This 0 represent x. What I say with respect to x, copy, paste, dxx. So 0 partial derivative with respect to x, then with respect to x or d2 f over dx dx. Copy, paste. Now auto numerical result f x 1 TNA differentiate. We pass 0. 0 represent the first variable x. We pass dx. It means we are going to differentiate f with respect to x. We get this f, this lambda from here. Then I will define another variable, size t and 5 points. So n here auto range sed array from 1.0 or 0.0 to 5.0. This is range, or I say bound. So bound. Then 1.0, 2.0, 3.0. 1.0, 2.0, 3.0 represent x, y, z coordinates. Copy, paste. Now A for algebraic result. We use evaluate. We don't need dx. Instead, we pass fx here. In this case, NR stands for numerical result. numerical derivatives. This is algebraic derivative. So we calculate numerical derivative with respect to x. In this case, we use algebraic derivatives. Stream nr f x1 nr f x1 and then copy paste algebraic result AR. Now I will scroll up. I would say 1. With this, in the command prompt, we rebuild CLSD. In this case, we used numerical derivative. In this case, we used fx algebraic derivatives. 0, 2, 3 represent coordinates. 0 represent the result of derivative, partial derivative. This is another point, next point, etc. So, numerical derivative, algebraic derivative, numerical derivative, algebraic derivative, numerical derivative, algebraic derivative matches, or we can make precision bigger. Stream STD precision we will set 15. We build again. CLSD. Now we can examine numerical derivatives with algebraic derivatives. This is 15 digit. So up to this point, our numerical calculation is correct. For example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Up to 12 digits, our numerical derivatives are correct. In this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 digits. In this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, up to 12 digits. Our numerical derivatives are very accurate. In this code, 0 means that we are going to use bound as a range of x because 0 represents the first variable x. In the same manner, this 0 means we are going to use bound defined here as a range of x because 0 represents the first variable x. In this bound, 0 and 5 are inclusive. Also, in this case, 1.0 represents x coordinates. This x coordinate is ignored because we use 0 that represent variable x. But 2.0 for y, 3.0 for Z. These two coordinates are fixed. In this result, 0, 0, 5, 5. Coordinates of x changes from 0, 1.25, 2.5, 3.75 up to 5. This 5 is inclusive. 5 points. So 1, 2, 3, 4, 5 points. In most applications, we can simply use default precision. Now I will copy, paste it here. I will change it to NL. Now we use dxx. So we are differentiating with respect to x twice. In this case, fxx. fxx. I would say xx, 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 xx. I don't need this number. I will fix like this. Also here, I will fix like this. Now with this, we build again. Sorry, I have to fix this one too. Now I will set it 1, 1. It means we are going to use this bound for y coordinates. So 2.0, 2.0. Y's coordinates are ignored. This value and this value are ignored. With this, we build again. CLSD. Now pay attention to these two cases. We set 1. So 0, 1.25, 2.5, 3.75, then 5. The coordinates of y-axis are changing. This is numerical differentiation. This is algebraic differentiation. They matches. Now I will copy this function, paste it here. I will rename SYCL. This is two generic parallel derivatives with SYCL. I will change it L. Now we need SYCL Q or device Q get device stream computing device get info SYCL info device name. Don't miss parentheses. SED and L. Now we have to use Q because we are going to use SYCL device. We simply put Q here. Copy, paste. paste. I pasted Q before lambda function. Now I will copy this function, paste it in function main. We build CLSD. In this case, we used CPU-based parallelism using Intel TBB. In this case, we used graphic device. This is numerical derivative. This is algebraic derivative. This number is very close to 0, so 0. And this result, matches. Also, this is second order partial derivative with respect to x. This is first order partial derivative with respect to x. In this case, 1, 1, the coordinates of y is changing like this, but x, z, x, z, x, z, x, z, the coordinates of x and z are fixed. Now, n to 10, or here also 10. Then we can compute at 10 points CLSD. So in this case, using CPU parallelism. In this case, using GPU parallelism. Now scroll up. In this function here, I will copy and paste f x, y, z. Now we differentiate with respect to y, then with respect to z. So this is partial derivative with respect to z, then y, then x. So I will create another one, dxyz. So it should be 0, 1, 2. It is d3 over dx dy dz. I will copy this part over here like this. Then we will copy this part, paste. Now f x y z it should be dx dy z f y z. This is x y z x y z x y z x y z. Now copy this part. we can paste it here. I will make it L, X, Y, Z. We need to provide Q right before lambda function. I made typo here. Also, I made typo here. Now we build again. CLS. I made another typo here. Also should be fixed. Now we build again. CLSD. So this is numerical differentiation. This is algebraic differentiation with respect to x, y, z, partial derivative.